students. Today we will discuss about the geometry of coordinate complexes. It will help to understand the metal and ligand relationship and its orientation in space. Some of the examples are written over here. Nickel with 4 chloride ions, platinum with 4 cyanide ions, and copper with 4 chloride ions. As you are already aware of that the metal ion present over here are called CMI, central metal ion, and the species written here in the small bracket or like this are called ligand. So in this lecture we will try to find out how these ligands are bonded with the CMI and what is the orientation of this species in space. So with the help of valence bond theory we will try to understand. See, about this topic, so many questions are asked in exam, like identify the coordination number of the complex, identify the hybridized state and what type of a hybridization present in particular example, and what will be the geometry of the particular complex, or compare the geometry of two complexes. And the last topic is magnetic behavior. You have to predict the magnetism, whether the substance is paramagnetic or diamagnetic. So with the help of valence bond theory we will try to solve all these problems. Here in VBT you are already aware of that valence bond theory prefer to form a covalent bond, and this bond is formed by overlapping of orbitals. Before overlapping of orbital, the central atom should get hybridized, and we are already aware of that before overlapping intermixing of atomic orbital will occur. So this is particular term, intermixing of atomic orbital, is also called hybridization. So we can say intermixing of orbitals and overlapping of orbitals will occur in central metal ion, and then this ion will provide vacant orbitals for the incoming ligand, and then metal and ligand bonding will occur, because ligand is going to form a coordinate linkage with the metal. So metal has some empty orbitals, and to create an empty orbital hybridization will take place. So we will try to find out the hybridized state of all the examples. See, we are having variety of examples like FeCN6 4 minus and cobalt NH3 whole 6 charge plus 3. Similarly NiCO whole 4, and the charge over this particular example is 0. NiCN whole 4, where you can write the charge dinegative. So students, you can see here I have taken so many examples where the number of ligands are 6 or 4, because only 6 or 4 coordination number complexes are in your portion or in your course. Some of the examples of having 5 coordination numbers are also found, but in this lecture I'll try to cover all the complexes in which the coordination number is 6 or 4. So generally you will find all the complexes are formed by the combination of 6 ligands or 4 ligands. So here you can see if the coordination number is 4, by the time what will be the geometry of the complex. If coordination number are 4, it means it has 4 hybridized orbitals, and 4 hybridized orbitals are formed in sp3 hybridization or in d sp2 hybridization. As you are already aware of the geometry, related to sp3. In sp3 hybridization, the geometry will be tetrahedral, and in dsp2 hybridization, the geometry will be square planar. Similarly, in coordination number 6, the overall geometry will be octahedral, and there are two possibilities of the hybridization. It may be dsp2 or sp3. So, students, you may get confused that I have written here d2 sp3 and sp3 d2. The d orbital is written before sp3 in this particular example, and here I have written d after sp3. So we will try to understand what type of a hybridization is this. See, the common electronic configuration of all the metals in d block is n-1d 1 to 10 and ns2, np0 and nd0. So there is no need to mention p and d orbitals here, but I am trying to explain you something. That's why I have written like this. Otherwise, you will write n-1d 1 to 10 and ns2. So take an example of any particular atom like iron. Its atomic number is 26. So its configuration will be, last electronic configuration will be 3d6 4s2, and here you will be having 4p and 4d empty orbitals together.